All right, so we are finished with our factoring chapter, and we're going to be moving on to a new chapter. We're going to skip around a little bit. We're actually going to move on to chapter 11, which talks about rational functions and equations. So before we get into the first section here, I just want to quickly talk about what a rational function is. A rational function, if you remember earlier in the year, we talked about all the different types of numbers. One of those types was a rational number. A rational number is any number that can be written as p over q. So basically any fraction, okay? We can have any number for p, any number for q, as long as they're whole numbers. So, 3 over 2, that's a rational number. 4 over 1, that's a rational number. 2 over 5, that's a rational number. So we're going to be seeing a lot of fractions in this chapter. So we have to make sure that we are kind of up to date with how to work with fractions, but we will be going over all of that in this chapter. But to start off with, we're going to be talking about what we call inverse variation. Okay, so let's get this here, inverse variation. Now, if you remember earlier in the year, we talked about something called direct variation. And direct variation, I'll put that off on the side here. Direct variation was anything that was in the form y equals kx. Okay? Well, inverse variation is very similar. We're really only going to be changing one thing here. Our inverse variation is going to be y equals k over x. Okay, so instead of it being a direct variation, it's now inverse, meaning we have a rational number here. So we're going to have a k, which is still our our constant of proportionality, or our constant of variation. Remember, we called that the k the last time. And then y and x are just going to be our two variables. All right, but k is still our constant of variation. So the first thing we're going to want to do is we're going to want to determine if different functions are inverse variations of each other. So, for example, if I gave you a table here, all right, I gave us an XY chart, and I have the points here 1 and 16, and we have 2 and 8, and 4 and 4. And I would ask you, is this an inverse variation, or is this a direct variation? Well, all we have to really do is check them, test it out. So first I'm going to test our new idea of our inverse variation. So all I'm going to do is I'm going to replace the x with my x. I'm going to replace the y with my y. So I'm going to get 16 equals k over 1. And what I need to do here is I need to solve for k. As long as k is the same in every single point, then it's that kind of variation. Now, obviously, we're testing inverse variation. So if my k's are all the same here, when I put it into the inverse variation, that means it's an inverse variation. If they're not, I'm going to check direct variation. If I plug it into the direct variation equation and all my k's are the same, then it's a direct variation equation. So let's solve for k here. If I were to solve for k, I'm going to want to multiply both sides by 1 to get rid of the denominator. So I'm going to get that k is equal to 16. So let's try the next one here. If I plug this into y equals kx, I'm going to have 8 equals k over 2. To get k by itself, I'm going to multiply both sides by 2. And 8 times 2 is going to give me 16. Okay? Do the same thing for the last one. I'm going to plug in 4 for y and 4 for x. I'm going to look to solve for k. Multiply both sides by 4. And again, I get k is equal to 16. So because we see here that we got k in all three instances, that means that this is an inverse variation. All right? So, again, as long as you test it into the function, and see if it works in whichever one, whether it be inverse or direct. The k has to be the same for every single point, and if it is the same, then it's that type of variation. If it's not, test the other one and see if the k is the same in that one. Now, I could also give it to you as a function, meaning I could say, let's test to see if x equals 2y is an inverse or a direct variation. Well, it's very simple. If I give you a function, we need to make it y equals, because if we look at both of our variations here, they both have y equals. They both start with a y equals. So all I'm going to do with the function here is I'm going to make it y equals. So in this function in particular, I want to get the y by itself. So I'm going to divide both sides by 2. So when I divide both sides by 2, this 2 cancels out. I'm left with y over here. This I'm going to leave as x over 2. Okay, and I'm just going to flip this around so that the y is on the left-hand side. So I have y equals x over 2. Now, you would think that this would be inverse, right? Because if I look at inverse, we see, oh, look, it's got a fraction here. But that's not the case. You have to be very careful with this. K needs to be on top. K needs to be in the numerator. K is the number here. K is the 2, right? The x and the y. The x has to be in the denominator, and the y is obviously on the other side. Here, my k is the 2 in the denominator, which really, when I rewrite this, is 1/2 x. This is a direct variation. Okay, so you have to be careful with that. The number has to be in the numerator in order for this to be an inverse variation. It can't be in the denominator. If it's in the denominator, it's a direct variation. Okay, so you have to be very careful with that. Alright, so very quickly I've got 2 problems up here on the board for you. I'd like you to take about 5 minutes, pause the video, and just determine if these are inverse or direct variation equations. Okay? So go ahead, take about 5 minutes, pause the video, and test these out. So as we see here, the first problem is going to be an inverse variation. When I plug it into my y equals k over x, here I multiply both sides by 1, I get k is 10. Here I multiply both sides by 2, I get k equals 10. Here I multiply both sides by 5, I get k equals 10. And because my k was the same on each one, and I used the inverse variation formula, the y equals k over x, that means it's an inverse variation. For the second one, I just rewrote it so that the y was on the left, so y equals negative 2x. This follows the direct variation equation of y equals kx. There's no fraction, the k is not on top, so this is a direct variation equation. Alright, so now we're going to look to actually write specific inverse variation equations. So let's say I wanted you to write the inverse variation equation. So let's say we wanted to assume that y varies inversely as x. That's not spelled correctly. Is it? Nope, there's supposed to be an E there. Sorry about that. So y varies inversely as x. Okay, and this is an important sentence right here. Y varies inversely as x. If we see this, the first thing we need to realize is that, okay, my function is going to follow the equation y equals k over x. That has to be our first thought. If we see y varies inversely as x, the first thing you should write down, y equals k over x. Then we can move on to the rest of the problem. So now the rest of the problem says, if y is equal to 18, when x is equal to 2, write an inverse variation equation. Okay? So now we just want to write the equation. Again, this is the main part here, the fact that we know that it's an inverse variation, that y is equal to kx, because now I'm just going to plug the y and the x that they give me in. So I'm going to take this y of 18, I'm going to plug it in for y, so I get 18 equals. I'm going to take the x that's 2, I'm going to replace it with the x here, that's 2. So the only thing that's missing is k. I need to solve for k. But it's very simple, it's exactly what we had done before. To get k by itself, just multiply both sides by your denominator. So we're going to multiply both sides by 2. So 18 times 2, that's going to give me 36. So I know that k is equal to 36. Now the last thing I do is I just take this k that we just got and plug it back into this original y equals kx. Don't change the y. Don't change the x. Just change the k. Leave y as y. Leave x as x. We'll make k what we just got because we want a function. A function has to have y and x in it. So this gets rewritten as y equals 36 over x. That is the inverse variation equation if y is 18 when x is 2. This would be the equation that I am looking for. Alright, so again, I've given you a problem here. I'd like you to take about 5 minutes. Take this, write the inverse variation equation. If y varies inversely as x, and if y is 5, when x is negative 4. So pause the video, take 5 minutes, do that problem, and then unpause it, see if we got it correct. Okay, so this should be the answer we get. Again, we see that y varies inversely as x, so we're working with y equals k over x. We plug in the y as 5, the x is negative 4. We multiply both sides by negative 4, so we get that. Negative 20 is k. So then I just replace the k with negative 20, and I get the equation y equals negative 20 over x. Okay, so let's say they're not asking for the equation. Let's say they just want to know a certain x or y value. So let's say the problem asks us, again, to assume that y varies inversely as x. And let's say this time we say if y is equal to 3 when x is equal to 12, here now we want to find x when y is equal to 4. So this is a little bit of a different problem here. It's not asking us to write an equation. It's asking us to find a variable. So if it's asking us to find a variable, it actually makes it a little bit easier for us, because we just know that our k's in both situations, for the y being 3 and the x is 12, and then the other situation where we don't know x and the y is 4, the k's have to be the same. So we actually get to use the equation y1 x1 equals y2 x2. Now again, if you don't remember what 1 and 2 mean, the y in the x1 is the first scenario. If y is 3 when x is 12, this is y1, this is x1. Okay, in the second scenario, this would be x2 and y2. So you just have to keep the numbers together with the first and the second concepts. But now all again I have to do is just place it into this equation. So I'm going to say, all right, y1 is 3, x1 is 12, y2 is 4, and x2 is x. And now I just solve it. So I have 3 times 12, that's 36, equals 4x. Alright, now I just take that 4x, I want to divide both sides by 4. So 36 divided by 4 gives me 9. And that's my answer. So what is x when y is 4? Well, x is going to be 9 when y is 4. So as long as you follow this equation here, if they're asking for a specific variable, it makes your life pretty simple. Alright, so the last thing I want to talk about, I'm not going to have you actually graph these inverse functions just yet, possibly at all, but we'll see. But I definitely want to show you what they look like. So I just want to bring back what our direct variation equation graphs looked like. Okay, so if we remember, a direct variation equation was one that always went through the origin, and it was always a straight line. Okay, so this was a direct variation equation. Now, we could have had it in different angles. It could have went up her further or faster. It could have came down, but it always went through the origin, and it was always a straight line. Now, inverse variation functions, they're going to look a little bit different. Okay? Inverse variation functions will always look something like this. They're always going to have one, I guess you would call this like a half, almost like an exponential graph going down. But then it's also going to be on the other side as well. So it's almost going to look like this, one half here type graph. Now, it could also be like this and like this. It could also be going that way. But it's always going to be this two-sided graph almost. You'll always have one here and then kind of one on the opposite side looking very similar to it. It could be moved up, it could be moved down, any of those things. But this is what a inverse variation graph looks like. And again, all that we would have to do if we wanted to graph it, we would take a bunch of points, take like -1, -2, -3, -4, 1, 2, 3, 4, plug it into the function, and then just plot the points that we would see, and we should see a graph similar to what we see here.